Hello everyone, welcome to A plus BI. This channel is all about complex numbers, and in this video we're going to be solving a very complex equation. Why do I call it very complex? Because -1 is at the base, we have a complex exponent, and the result is a complex number. How complex can that get, right? So we're going to solve for z here, that's our goal. How do we solve for z? I'll be presenting two methods. Okay, let's start with the first one. For my first method, I want to use the polar form. So let's go ahead and write -1 as a complex number in exponential form using Euler's formula. What is Euler's formula? Euler's formula says any complex number z or w, whatever, can be written as r times e to the I theta, where r is the absolute value or the modulus and theta is the argument, okay? And argument basically means the angle, so if you graph it or plot it, whatever, this is the theta, and r is the distance from 0, quickly, right? If you're new to complex numbers, and if this looks a little hard to you, go ahead and check out my lecture videos. I also have another channel called Cyber Math, Number Theory, and Algebra. Okay, now let's go ahead and check how we can solve this problem. I'm going to start with -1. -1 is actually going to appear here, 1 unit away from 0, so it's going to be e to the power I. The argument is going to be pi, so I'm going to multiply by pi, but I'm also allowed to add 2 pi n. N is an integer, because multiples of 2 pi is just going to give us a full rotation, which brings us to the exact same point. So infinitely many values that you can use, okay? So that's why we want to express in a general form. But we need to raise it to another power, so let's do it. We're going to take that and then raise it to the power z plus I, right? And that's equal to 1 plus I. Let's also go ahead and write 1 plus I in polar form. If you think about it, 1 plus I is going to be here, making a pi over 4 radians, right? That's 1 plus I. From the Pythagorean theorem, the modulus is square root of 2. And the angle is pi over 4. But again, we want to express it using another integer, 2 pi k. K is an integer, okay? Cool. Now, what do we do? Exponentiate, right? So let's go ahead and multiply these. By the way, does this rule always apply? What are some exceptions? And so can we safely say that a to the power b to the power c does not always equal e to the power bc when b, c are complex numbers, or under which conditions this is not going to work? And if this doesn't work, how do we solve this equation without using that property, right? Is there another property? What do you think? Anyways, comment section down below. So let's go ahead and pretend that this property applies and multiply everything. That's a 2. That's a z plus I. And then we can go ahead and write this. And now we have e's on both sides. So there's a couple things we can do. First of all, we can go ahead and subtract the exponents, but there's a better way to do it. Let's get rid of e, shall we? So let's use natural log. ln here and ln here. That's going to give us the exponent, which is I pi plus 2 pi n multiplied by z plus I equals, now when you ln this, you're going to get ln root 2, plus when you ln this, you're going to get the exponent one more time, because ln e is 1. And then eventually we're going to bring these imaginary parts together anyways, right? But this is multiplied by z plus I. So how do we do this? Nicely. I think a better way to do it is isolate the z. There's no reason to distribute or subtract. Let's go ahead and divide, because division is going to almost isolate z plus I. So we're going to get this plus I times pi over 4 plus 2 pi k divided by I times pi plus 2 pi n. By the way, we may not need all these integers, but I just wanted to write it just to be on the safe side. I is gone, and then we can simplify this, okay? Let's do it, and then we can take care of I at the end. But let's multiply by -I. That just bothers me here. So that's going to give us 1. We have a -I So let's see. I could probably write this as, let's switch the real and imaginary part, shall we? This is gonna be 8 pi k plus pi over 4 divided by pi plus 2 pi n minus I times ln root 2 over pi plus 2 pi n. Okay, now we can factor out pi actually, put the 4 at the bottom. So that's going to look like this. Imagine you already canceled out the pi, so you're going to end up with 8k plus 1. And the 4 is going to be written at the bottom, multiply by this. That's going to be 4 plus, or I should probably write it the other way around. When I multiply this by 4, it's going to be 8n plus 1. Because pi is gone, remember, we factored it out. Minus I times this stuff. Okay? Cool. Now, what do we do next? Maybe get rid of the I, subtract I from both sides, and we should get that. So now our imaginary part is slightly modified, right? And we can kind of write this as mainly minus I times this plus 1 because we negated it already. And if you want to factor out a pi, like write it this way, that's perfectly fine. You don't have to, but you can also write it like this. Cool, cool. Now, what does this mean? This kind of looks confusing, right? But we can go ahead and replace k and n with 0 at the same time to get the simplest solution, simplest looking at least. 1, nice. The real part is 1, and then we have an imaginary part, but this is going to be ln root 2 plus 1. We can simplify this, but that's not necessary. It will be pi here. So, kind of like a complex number in standard form, 1 a plus bi, but that's just the principal value because there are infinitely many values up to n and k, right? So where do we go from here? We can actually go ahead and take a look at another method, an alternative, okay? So let's call it second method. So now we have, it's probably not going to be maybe slightly different, okay? So we have z plus I. Maybe I can separate this. And I kind of think about the meaning of -1 to the power I. But in order to simplify this process a little bit, can I just write this as e to the power I pi so that I can get something a little nicer from here? So now -1 to the power z times, right? Times e to the power I squared pi, which is e to the power -pi, equals 1 plus I. And then from here, I should end up with -1 to the power z equals 1 plus I divided by e to the power -pi, which can be written as e to the power pi times 1 plus I. Nice. And then from here, can we solve for z? Probably by using the polar form or the natural logarithm, we should be able to solve it. But is that going to give us the exact same answer? That's for you to find out. But that's what I got so far in general form. It's more like this. Now let's go ahead and check Wolfram alpha, and we'll finish up with that. And ta-da! Wolfram alpha gives it in the form of log 1 plus I, which we can actually evaluate with the complex logarithm. And this brings us to the end of this video. Thanks for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe, take care, and bye-bye.